a start for today's Marine Robotics reading group. So as usual, we have the catering, so please help yourself at the back there. And today we're really lucky to be joined by Hui Sheng. So Hui Sheng is at CSIRO. He's a research engineer working in marine engineering, and he specialises in developing autonomous marine systems for ocean observations. So I'm really looking forward to his talk today. Thank you so much for joining us. And it's going to be on the topic marine autonomy from algorithm to observations. So can everyone please join me in welcoming Hui Sheng?
Thank you for the introduction, Scarlett. Can everyone hear me all right?
Yeah.
Awesome. Yep, I'll make a start now. So everyone, I'm Hui Sheng. I'm a marine research engineer with CSIRO, based down in Hobart. My work sits at the intersection of engineering and science. And today I want to share with you how we're using the autonomous marine systems to collect meaningful scientific observations. I'll take you through a bit of our journey from tech algorithms to real-world deployments and show how these systems are starting to support various science missions. So to kick things off, let's talk about marine observations, which is really the focus of my talk today. Collecting data from the ocean has always been a challenge, and traditionally we rely heavily on crew research vessels. They're effective, but they're also expensive, resource heavy, and not always available when you need them. And to scale things up, we also have a global network of in situ sensors like moorings, cargo floats. They've been incredibly valuable, but they work in a passive way. So they sit and wait and aren't well suited for capturing small scale or short-lived phenomena. But many of the things we care about in the ocean, like tracking the abundance of critically endangered hamfish here in Tasmania, identifying coral field maxima in the water column, things like that, they don't always happen when and where you expect. Same goes for harmful algae blooms, marine heat waves, etc. Take the recent algae bloom outbreak in the South Australia, for example. It affected fisheries, tourism, ecosystem across a wide area and caught many off guard. If we want to detect and respond to these events in a timely way, we need more flexible, intelligent systems that can decide where and when to sample and do it at sea autonomously. So this is where autonomous marine systems come in. These platforms that give us a more cost-effective way to carry out repeated surveys that can operate over longer periods and wider areas, which means we are able to capture spatial and temporal patterns in the ocean much more effectively. They're also safer. They can go to remote locations, work in rough weather, places that would be difficult, dangerous, or just too expensive to reach with a crew vessel. And if you take a look at the map here, you would see just how vast Australian marine regions are, especially when we're talking about monitoring our marine parks. And so to do this at scale and in a sustainable way, we need to use autonomous systems as part of the toolkit, helping us to do more with less and in a more eco-friendly way. So right now, most commercial autonomous platforms that still work in a pretty simple way. An operator loads a set of waypoints, usually in a lawnmower style grid, and the vehicle which just goes off and follows the path. And when the data come back, if the coverage isn't good enough, we give it another batch of waypoints and send it out again. So it's basically an open loop process. Plan, run, check, and repeat. That's fine for a static, well-defined patch of seafloor. But if the things you're interested in is moving, like a patch of plankton, a school of fish, or a slick of bloom, the vehicle can sail right past it or only collect a handful of sparse data points. And because someone always has to babysit the mission, we often end up with more human operators, more personnel on the boat than the vehicles in water, which is kind of defeats the purpose of going autonomous in the first place. So why are we not there yet with truly autonomous marine systems? The short answer is the ocean makes everything harder. So unlike ground or aerial robots, we have to build a system that can handle waterproofing, higher pressure, corrosion, biofouling, and a constantly changing dynamic environments. There's also very little navigation support underwater, no GPS, no landmarks, and poor visibility. Electromagnetic signals and even light get absorbed quickly in the water, which means we are limited to things like acoustic for communication and positioning. So that slows everything down and makes real-time decision-making much trickier. So it's no surprise that marine autonomy has been slower to progress compared to land or aerial systems. But despite these challenges, we do know what the end goal might look like, and we're starting to build towards it. So the vision here is to increase the level of autonomy in this system. We want marine robot that can do more than just follow a preset path. We want them to sense their environment, understand what's happening, and make smart decisions in response. A big part of this is adaptive path planning, letting the vehicles plan their path on the go, constantly refining and adjusting their behavior as the conditions change. This helps make sure we're collecting the right data at the right place and time. And a key focus is on data persistence, basically making sure we can generate continuous, reliable data over time, even for dynamic or rare phenomena. But we don't stop at single robot. We're also looking at scaling this up to multi-vehicle fleet planning, getting different platforms to work together to improve our spatial and temporal coverage, and to support more complex scientific goals. And finally, we want our solution should work across different systems, different vehicles, and be reusable in different scenarios, from like tracking marine heat waves to surveying reefs, detecting algae blooms, etc. So that brings us to one of the key research areas I'm working on, informative path planning. We know that in the ocean, some bits of data are just more valuable than the others. For instance, scientists often most interested in peak values, like the warmest water, the highest chlorophyll concentration, the most extreme values. So instead of just sending out a robot to blindly cover an area, we wanted to collect the right information in the right place. That's what informative path planning is all about, guiding the robot to gather the most scientifically meaningful data based on what it's learning as it collects observations from the environment. The challenge here is that the robot starts off knowing almost nothing. So this plot here shows the ground truth, what the environment actually looks like, but the robot doesn't get to see this. What it might have is a rough idea of how the phenomenon behaves, maybe the general scale, the expected ranges of values, but not the actual spatial distribution. So what we want is for the system to explore, take a few samples, and then update its prediction on the fly. It can then steer itself towards the area that look promising, like this the red X cross here, which marks the global maximum in the field. The idea is to persistently track this high value spot and continue refining its path as it collects more observations. So instead of just a static pre-planned path, it becomes an adaptive process, constantly adjusting based on incoming information with the goal of maximizing information gain. So how do we implement informative path planning in practice? The technique we've chosen is a variation of Monte Carlo tree search, or MCTS. It's a powerful search heuristic that helps the vehicle explore different path options in a structured but flexible way. At its core, MCTS builds a tree of possible future paths using focused random sampling. This allows it to focus on the most promising trajectories, the ones likely to give us the highest information gain. So one of the reasons we use MCTS is because it's an anytime algorithm, which means we can stop the planning process at any time and still have a usable solution. And if we have more time or more computation power, we can keep expanding the tree and potentially finding better paths. Another key advantage is that MCTS is reward function agnostic. It doesn't care what metric we are optimizing as long as we define the reward properly, whether it's finding the warmest water, peak chlorophyll, or anything else, MCTS can work with it. This flexibility makes it a great fit for science-driven autonomy, where the objectives can vary depending on the mission. To drive the planning behavior, we combine MCTS with a set of reward functions based on Bayesian optimization. These reward functions help the system estimate where it's most valuable to go next, not just randomly, but in such a way that it balances exploration and exploitation. So we're not only learning about the environment, but also actively tracking high-value targets. Together with MCTS, these reward functions form the core of our algorithm. To test how this works, we set up a range of simulation scenarios using this algorithm. The goal here is maximum localization. We want the vehicle to find the peak value in the environment, which is shown by the red cross on this plot. The environment itself is generated as a Gaussian field. This gives us a continuous, spatially correlated surface that mimics how normally biogeochemical parameters would behave in the ocean. And here we compare two strategies: the informative path generated by our MCTS-based algorithm and a standard lawnmower path, both covering the same distance. To test whether planning for information actually gives us an advantage in finding the hotspot compared to just blindly sweeping the area. So let's walk through what the simulation looks like in action. So here is a pretty challenging scenario. The vehicle starts in a location that's surrounded by low values. As it begins exploring, it gathers more data, but it's still all looks pretty low. So the algorithm needs to make a decision here, stay or keep sampling in this low value region, or to try to move up to search elsewhere. And because the planning algorithm updates based on new information, as you can see in the reward map on the right, it gradually builds enough confidence to push further out. So eventually the algorithm identifies a promising direction and navigates towards the region that are more likely to contain the maximum. So at this point, the vehicle see a potential region of high values, and you can see that being highlighted in the reward map here. And then it decides to go check out this region, but it turns out it's still not quite a peak. So it continues exploring using the updated information, and you can see finally it converges at the global maximum again. You can see this shows up on the vehicle reward map as well. Now if we compare this to the lawnmower path of the same length, that's the one on the top, we can see that it completely missed the global maximum. So that's the key limitation of non-adaptive path. They don't respond to new data, and as a result, they might miss important features like this peak here. Finally, here's a comparison of the estimated environment built by the two approaches side by side with the ground truth. You can see clearly that the adaptive path has built a much more accurate model, especially in the high value regions, which is exactly what it was set up to do. So that's the strength of this approach. By actively seeking out the most informative areas, the vehicle builds a more useful understanding of the environment, not just a blanket coverage. So, so far, everything I've shown has been for single vehicle, and coordinating multi-vehicles effectively, it's a whole new challenge, especially in environments where communication is limited, like underwater. So the usual approach for multi-vehicle planning is to have a central planner, like a mothership, that decides everything for all vehicles. But that relies on stable, continuous comms, which is not something we can count on in the ocean. So instead, we've gone with a decentralized version of MCTS, which we call DEC MCTS. So in this approach, each vehicle runs its own MCTS planner. They don't need to share all the raw data with each other, just bits of information about the actions they are planning to take. So at the beginning, you can see each vehicle assumes the others are just taking random action and builds its own tree. Once they work out a distribution of promising actions, they share that summary with the rest of the fleet. Everyone then re-expands their own tree based on what the others are more likely to do. And finally, these cycles repeat in an iterative optimization process. And because the shared info is lightweight and occasional, it works even with sparse communication. And best of all, the computation scales linearly with the number of vehicles, so we can scale to fleets of 10 or even more vehicles. So rather than just relying on a central controller, each vehicle is doing its own planning, adjusting in real time to the behavior of others, making the whole system more robust and scalable. Now, to support this kind of decentralized multi-vehicle planning, we also need a good way to measure how informative each vehicle plan is, not just individually, but as a group. For that, we developed a joint informative reward function, which we call JMES, short for Joint Max Value Entropy Search. JMES is designed specifically for multi-agent maximum localization tasks. What makes JMES powerful is that it doesn't just look at each sampling location in isolation. It actually accounts for the correlations between multiple locations across all vehicles. That means we're not double counting redundant samples, and we can better coordinate sampling across the fleet. This is especially important in a multi-vehicle setting where you want to maximize the joint information gain, not just each vehicle acting greedily on its own. So with that MCTS using JMES as the reward, each vehicle plans locally but with a global objective in mind, which brings us much closer to robust and scalable multi-vehicle coordination. To demonstrate this approach, let's look at a multi-vehicle simulation scenario for maximum localization. So now in this scenario, the environment again follows a Gaussian distribution, but this time we make things a little bit more complex. So instead of a single peak, we introduce multiple peaks of different values with one global maximum marked by the red cross here. We're setting up 3 homogeneous vehicles, all running the decentralized planner using the JMES reward. As before, we compare the performance of the adaptive informative planner against a standard lawnmower pattern, both with the same total path length. This lets us see how well coordinated decentralized planning performs when it comes to locating the most important features in the environment, in this case, the highest peak here. So here's what it looks like in action. One thing that stands out straight away is using multiple vehicles really speeds up the whole data collection process. And early on, one of the vehicle you can see finds a region with a fairly high value. You can see that reward map on the reward map. This area looks pretty promising and get a pretty good score. But not long after, another vehicle stumbles across an even higher value region. The reward map get updated accordingly, and now the previous high area is downgraded, and the new location takes over as the most likely spot for the maximum. And the fleet continues to explore the field, adjusting their priorities as new information come in. And you can see at this point, we see two vehicles heading towards each other into the same area. This is where coordination becomes important. They need to resolve overlap and decide who goes where. So one of them decided to head south, ending up finding another very high value region. And again, you can see the reward map updated. And now we got two strong candidates for the global maximum. And finally, let's look at the estimated model produced by the adaptive versus the lawnmower approach. The lawnmower paths cover the field reasonably well, but they miss the global maximum. And as a result, you can see the model built from this data ends up underestimating the peak value. And the adaptive approach allows the fleet to concentrate sampling effort around those high potential areas. In this case, the adaptive strategy successfully detect the global maximum, and the estimated peak value is much closer to the ground truth. This shows how adaptive information-driven planning can significantly improve both the accuracy and the efficiency of multi-vehicle data collection, especially in scenarios where the goal is to locate features like peaks or anomalies in a field. All right, now that we've seen how the vehicles behave and how the environment can be reconstructed visually, let's look at how we evaluate the algorithm more quantitatively. So what we want to know is, did the algorithm actually help us find the important regions, especially the ones with high values? So to do this, we turn the problem into a simple binary classification task. For both the ground truth and the estimated model, we classify each location as either high or low value. So a point is considered high value if it is greater than 95% of the global maximum. Everything else is labeled low. So you can adjust this threshold depending on the scientific requirements. And with that, we can build a confusion matrix showing how many of the high value points were correctly found and how many were missed and so on. And from there, we can calculate recall, which is a metric, just a fraction of the actual high value regions that were correctly identified. So if the algorithm finds all the important peaks, we get a recall that's close to 1. So this gives us a useful interpretable number to compare different path planning approaches, especially when it comes to finding those important features that we care most about. Using the recall metric, we can explore how the algorithm performs under different settings. Here we're looking at a violin plot of recall scores for different number of MCTS iterations, ranging from 1 iterations up to 200 under different noise level. Starting from the left, 1 iteration basically means we are making decision completely random. That gives us a baseline. This is what we would expect if there were no intelligent planning at all. As we increase the number of iterations, the algorithm has more time to evaluate possible paths and make better decisions. And we can see the recall improves significantly. And now what's interesting is that around 50 iterations, we start to hit a sweet spot. The recall is consistently high, and the variation across the run is quite low under both noise setting. That means the algorithm not just performing well, but also pretty robust. So going beyond that, say 100, 200 iterations, that doesn't quite give us more gain, but it does cost more in terms of computation. So overall, 50 iterations gives a nice trade-off between performance, consistency, and efficiency. And now let's look at how the algorithm converges over time towards the global maximum. Here I'm showing the mean absolute error, MAE. That's the difference between the highest value observed by the vehicles and the true global maximum, plotted against the distance travel. We got 3 settings here. Our algorithm under 2 different noise conditions, 3 and 10%, as well as the baseline lawnmower approach. You can see the solid lines here show the average error over 50 repeated runs. The shaded regions is the standard deviation, and the dotted lines show the worst case performance in each setting. You can see that our algorithm consistently converges faster and with better accuracy, even in higher observation noise. The high noise version does show a little bit more variability, which is expected, but it still stays well ahead of the lawnmower path, even in the worst case. And if you look at the final mean absolute error achieved by the lawnmower, you'll notice something interesting. Our algorithm actually hits the same level of performance with only about half the distance traveled. So that's a big win in terms of efficiency. We're getting better results with significantly much effort. All right, to wrap up the evaluation, let's take a quick look at the broader comparison across different algorithm configurations and reward functions. On the left, we got the recall score, so how well each combination did in identifying the high value regions. And then on the right is the computational time, how long it takes to run the algorithms. For the rows, we got different algorithm types. At the top is the baseline, which is completely random. And then we got myopic planning with one step look ahead, a rollout only version with no search tree, and finally full MCTS with different rollout policies. And along the columns, we vary the reward function used to guide the planning from simple mean to Bayesian functions like MES and JMES. And you can see that any MES and JMES that generally give better performance, they score higher on recall, but they also come with higher computational costs. So there's a trade-off. It's not just about picking the top performing one. You got to consider what's feasible given the time or onboard resources you have. So you basically got to pick your poison. Do you want better accuracy or faster computation? Finding the sweet spot between the two is what we aim for depending on the mission requirements. All right, now let's move from theory to practice and look at the hardware platform we are using. We got an ASV surface vehicle and a couple underwater vehicles or AUVs. The ASV we're using is the Marine Robotics Order, a catamaran-style surface vessel powered by twin electric drives. It weighs around 70 kilograms, so it's pretty easy to deploy with a couple of people. It's built to carry a range of scientific payloads, including a winch system that can lower sensors all the way down to 50 meters. It also supports multiple comms channels to talk to the base station, which is pretty handy in real time for monitoring and control. Alongside the ASV, we're also using the RTC's NemoSense AUV. It's a small torpedo-shaped underwater vehicle, about a meter long, weighs under 10 kilograms without a payload. So it's also very easily deployable with just a single person. It has a modular front payload section, which gives us flexibility to swap in different sensors depending on the mission. We're applying this platform and our algorithm to a range of real-world applications. One of the key applications is in tracking alkaline plumes as part of the ocean alkalinity enhancement experiments. This work was done in collaboration with the Carbon Log Future Science platform at CSIRO, where the aim is to remove atmospheric CO2 by increasing the ocean's alkalinity, typically by releasing substances like sodium hydroxide into the seawater. We've been using the Order ASV to support this experiment. Back in November 2024, we ran some small-scale pilot studies around Hobart using the ASV to monitor pH changes during controlled alkaline release. And the goal was to delineate the spatial extent of the resulting alkalinity plumes. The next step is to scale up, applying this method to larger experiments where we can better evaluate the behavior and the spread of these plumes under more realistic conditions. Another application we're working on is water quality and harmful algae blooms monitoring. So the idea is quite similar. We want to identify and track extreme values in the water quality parameters, and then decide where and when to collect water samples for further analysis. So this is done by a custom eDNA sampling system on board our Order ASV. The sampler, it can only take a limited number of samples. So efficient and targeted planning become really important. Locally, in Tassie, we're applying this to monitor recreational water quality at the Blackmans Bay. And we're also planning to extend this work to South Australia to monitor harmful algae blooms. This is especially relevant given the recent issues with the blue-green algae blooms in the region. We already completed some pilot work in Hobart using manual surveys and sample collection. So the next step is to move towards fully autonomous trials using the ASV to plan and execute the sampling task on its own. Another applications we're exploring is fish stock assessment, specifically using our Order ASV with some eco sounder to carry out acoustic surveys for estimating snapper biomass. Back in January 2025, we conducted a joint survey with SARD in Gulf St. Vincent, where the Order operated alongside a crew research vessel. The results show that the ASV can achieve a similarly good acoustic data quality to the crew platforms, which is really encouraging. And the next step is to make this mission more adaptive. We are working on integrating an automated optical survey system using a drop camera deployed from the Order winch. So this would allow the vehicle to collect additional visual data in real time, especially in areas where the acoustic signals suggest something interesting underneath. And the last application I wanted to highlight here is our work on hamfish survey locally in Hobart. So for those unfamiliar, hamfish is a critically endangered species found only along the southern coast of Australia. Traditionally, population surveys have relied on scuba divers and more recently some eDNA sampling techniques for the survey. We also use the SRV and ROV to carry out exhaustive mapping of non-habitats, which gives us a pretty good visual data, but still require a fair bit of manual effort. So to make this more efficient and eventually autonomous, we're now looking to move the survey capability onto our AUVs. So the setup includes a stereo camera system for estimating the fish sizes, and we're running an edge device on board with computer vision. And this work is done partly in collaboration with the University of Tasmania. We developed a detection model for automatic identification of hamfish. And the next goal is to deploy that model in a field trial. All right, so to wrap up, across all these projects, we've been showing how autonomy isn't just a technical novelty, but a practical tool for making marine observations more efficient and scalable. So these are just some early examples, but they show what's possible. Looking ahead, a big focus will be on running more field demonstrations and trials. These are critical not just for validating the tech, but also building confidence with users and collaborators. We're also scoping out broader applications, things like reef health or aquaculture monitoring, where autonomy can make a real difference in efficiency and repeatability. Another really exciting direction is to adapting some of this method to other domains like land-based or aerial system. We are currently working with other departments within CSIRO to apply the algorithm for critical mineral detections. Then there's integration to more platforms like SurfB or the Ranger bot from QUT, and the Seeker AUV from ACFR as well. So getting this system to coordinate effectively opens up more complex and multi-scale missions. And to support that, we are also investing in improving fleet coordination and tasking. And finally, you want to close the loop between autonomy and the science. That means making sure the decision this system are making about where to go and when to sample are really aligned with the underlying observation goals. Yeah, so that's where we're heading. Still a lot of work to do, but we are building the momentum and we're excited to see how far we can take it. So thank you everyone for your time. Happy to chat more and keen to hear your thoughts and questions. Thank you.
Thank you so much, Hui Sheng, for that fantastic talk. We have a bit of time for questions. So does anyone in the room want to kick us off? Alec? Oh, hang on a second. I'm just checking. I think the roof mic is it just straight up not working? Okay. I'm going to run this around.
Can you talk a bit more about, yeah, sure. Can you talk a little bit more about, for multi-robotics, in terms of the Monte Carlo tree building, as far as multi-robotics goes, exactly how much information needed to be shared between the robots in order to get reasonably useful collaborative behaviors?
It really depends on how much you can share, how much bandwidth you have. But about the action, it's basically you sampling the best. So with MCTS, you can sample the best solution when you want to finish the run. So you can actually sample the top 10 or top 20 actions that are more likely to run, and then you can rank the distribution, the action probability according to their rewards. So higher rewards, you can give it a higher probability, lower rewards, you can give the action a lower probability. So that gives you a distribution of possible actions. And because you can decide how many actions you want to share, that means it's pretty flexible, depending on your bandwidth. Of course, the more you share, the more likely the other robots can understand your actions.
Okay. For when that was going on, were all robots aware of the full map in terms of the estimation, or were they just only aware of their individual maps?
So as part of, depending on the bandwidth as well, so you can share part of your observation with the others. So that's one of the key limitation in this aspect. So the model that everyone's building, because if you want to take into account others' observation, you need to sample, you need the observation from the others as well. So you will need to share observations with the others as well in that sense. So you can also decide how much you want to share, like how dense the data point you want to share, or just a number of representative data points with the others. So we're also looking at using sparse GP for that aspect. At the moment, we just assume we can share the data points or the observation in simulations. But yeah, if you can use sparse GP or other GP that allows you to build model from less data points, then that will be more efficient in real life.
For your real life, I know just running the mic around might be a hassle. For real life experimentation on this, are you targeting a particular kind of communications technology, or is that yet to be determined?
I would say yet to be determined. We were looking at some very limited acoustic bandwidth with just about 56 bits of data per transfer, per share, per message, which runs at like a cycle of about 10 seconds. So that is pretty limited. But we are also looking at better acoustic technology as well. So at the moment, we don't have the hardware in the lab to verify with higher bandwidth to verify this. But yeah, it's something that we are looking to experiment as well in the field.
Okay.
I think going on the same line is like once you see another robot, for example, underwater, how do you localize each other? And does the localization, I can imagine localization in 3D space is difficult, and also sharing that information correctly would be difficult. So could you talk about how you guys do that?
So at the moment, we still assume we're doing 2D. We haven't gone into 3D yet. So, which means it's only applicable either on the surface or when you're doing a bandit mapping. So you can assume, like for bandit mapping, you can assume it to be a 2.5D kind of problem. And then, so your question was about how
would they share map information through because the localizations would be different
yeah.
for each one?
Yeah. So the localization problem. So at the moment in simulation, we just assume the localization was perfect. But in practice, with like USBL and all the other localization technique, because we're not exactly focusing on the localization aspect in this problem. So we can almost assume, then the location that everyone's sharing, like the action everyone's sharing, is where we expect them to be. And then if those information get corrected in the next, like say USBL cycle or the next resurfacing cycle, you can correct those information and share that again with the other vehicles.
Thank you.
Any more questions in the room? And then we'll go to online after these two.
Hi, Hui. This is Dorian Tsai speaking. Thank you very much for the talk. If you could go back to the slide about the sonar fish detection side of things, I had a couple of questions there. Sorry about that.
Right. Sorry, which slide again?
The sonar fish detection.
Sonar fish detection. Yep.
Yes. And I was wondering, yes, how did you actually detect all of the fish in the biomass, and then if you were able to apply your informative navigation for, like, say, moving towards the denser areas of fish, how is that, like, were you able to, like, measure the, I guess, the gain in your specific navigation methods compared to a lawnmower?
So for this, for finding the snapper, because they are gas bladder fish, so they have a very specific acoustic signature that shows up on the fish finder. So on the eco sounder, so you pick up those signature, and this is where the snapper are likely to be, and then based on that you can then estimate. So normally those snapper, they tend to aggregate around artificial reefs, which is like shipwrecks underwater. So if you look for sign of those shipwrecks or those acoustic signatures, you can know this is the spot where you're more likely to find these fish, these snappers.
Very cool. Thank you.
Okay, Serena, did you have a question?
Thank you. Really enjoyed your talk. Thank you for that. I have a lot of questions, but I'm just gonna stick to one, I think. So the question I had is about the scale of your adaptive search. So for your example that you have, your Gaussian spreads were, you know, maybe a third of, say, the width of your scale.
Yeah.
If your global maximums and the spread was a lot smaller, is there a point where if you were looking for things that were kind of more targeted, if a lawnmower at some point would a lawnmower be better?
Well, if you're looking at much smaller scale, I think that actually makes lawnmower, it might actually make lawnmower even worse, because that means you need to place your tracks really, really close together, and you end up with a really, really long path and long mission time. So, and for the adaptive path, you can adjust, depending on the length scale, you can decide how long or short each action would be. So, yeah, so with smaller length scale problem, your action that you need to decide will be of smaller length. That means the path will be more flexible to navigate around to find those high regions. And then for larger length scale, because you don't really need to make such a high resolution action scale. So that means you can make your action path actually longer, and then the planning can be more efficient.
Okay, thank you.
Did we have any questions from anyone that's still online? Doesn't look like it. Any last one from in the room? Okay, awesome. Thank you so much for joining us, Hui Sheng. And can everyone give him one more round of applause, please?